Okay, welcome back. I was not able to finish the next type of processor, so we're going to take a quick detour into arithmetic. This will actually help us in understanding how the different instructions can have variable length execution time. I mean, we've already seen this a little bit with add, where we've noticed that add can have a different type of gate delays depending on which type of adder you choose, but the other instructions like divide and multiply can also have a varying level of gate delays or cycle time depending on which implementation of multiply and divide you choose. Naturally, we've also talked about memory a bit, which can have a very diverse amount of cycle time. But right now, let's go and talk about arithmetic for computers. We're going to go through basically integer multiplication, division, and then we'll also do floating point, although floating point will be later on this week. Alright, so we have already talked a little bit about arithmetic because we've talked about addition and two's complement, so we're going to roll through that real quick, and then we'll get through multiplication, division, and how to deal with the overflow and floating point numbers. So we've already talked about integer addition, so we can skip this. This is just to show you that 1 bit or binary addition works just the same as our decimal base, except for you only have 2 digits. And we talked about two's complement, where we simply negate it and add 1 in order to get the negative, and so we're good with that. So some languages do ignore overflow. If you've ever programmed in C, which we have in last time, if you take an integer all the way to max and you add 1, it goes all the way to minimum. That's called overflow. Or if you go all the way to minimum and subtract 1, that's underflow. And so those two, C ignores what the errors are from there, because normally in some languages, I should say not normally, but in other languages that really care about program accuracy, like Ada, and I guess to some extent Fortran, they will actually raise an exception when this happens. There are different types of addition. Hopefully we'll get to this with graphics, but the idea here is that you may be wanting to do multiple additions at one time. For example, you have 8-bit or 16-bit data. If you have 8-bit data and you have a 64-bit adder, that means you can do 8 adds at the same time if you partition the array. And by the array, I mean the register into 8 sections, each 8-bit long. This is called something called SIMD. And the only problem with here is since each 8 bits is a section of the register, you have to deal with the overflow of each individual bit. But this is actually done a lot in computers. Alright, so multiplication. Over here on your right, we have our basic architecture for a simple implementation of multiply. Let's go over here and look at the numbers, the binary addition, multiplication, and let's do the example, and that should go help us what's happening. So the multiplicans, well, this looks like 1,000, but this is actually, I'm sorry, 1, 2, 4. This is 8 multiplied by 9. So you have 8 over here, and then you're going to have the multiplier down here right there, which is 9. Alright, so a couple things to look at real quick. Let's say that this is for a 32-bit multiplication. Notice that with 32 bits, the multiplicand is still 64 bits. The shifter is 32, and the product is 64. Now, and you have to have a 64-bit ALU for our 32-bit multiplication in this example, and we'll get to that in a moment. But the real thing that should jump out is the product definitely have to be 64 bits, because if you're multiplying a billion times a billion, that number is going to go and flow into the 64-bit range. It cannot be contained inside a 32-bit number. So when you are doing multiplication, your product or your final answer does need to be twice the length of your multiplicand and your multiplier. Although the rest of this, as we'll see in a little while, doesn't have to be 64-bit, but we're going to leave it 64-bit because I think this is a lot simpler. Alright, and again, I wish we had a board. So just pretend that 1,000 is in here, and 1,001 is over here. So the first thing we do is, do they actually label the steps? They do label steps. Oh, that's beautiful. Well, let's go do it visually first. So you have 1,001 over here. You're going to test if that last bit is 1. It is. So we're going to tell the ALU to take the product, which is currently 0, add it to the multiplicand, which is 1,000, and then store that in here. That's what this 1,000 is right here. All right, let's do this. Now we're going to shift down to the right. So that's going to, when you shift to the right, you take the 1001, you shift it this way. And when you do that, since the 1 was the last digit, it falls off or disappears. So the number you're going to have now is, once you've right shifted this by 1, will be 100. And so you test if that if the last bit's a 1, it is not. So what happens is the product basically gets added to 0 and back into product. And the multiplicand though is shifted left. So the multiplicand at this point does become 10000. And you'll see, they don't really write the zeros out here, but you'll see why that's the case in a bit. Now when you shift it again to the right, it was 100, now it's going to be 10 because that last 0 pops off. Again, it's a 0, so when it goes over here, it's just going to add it to itself. And the multiplicand is again going to be shifted up, so the multiplicand at that point will be 1 followed by 5 zeros. Then you're going to shift it one more time. It was 10, now it's going to become 1. And so since it is a 1, the multiplicand gets shifted up, since it is a 1, it is going to take the product, which is currently 1 0 with 3 zeros, and then add it to the multiplicand, which at that point will be 1 followed by 5 zeros. I'm sorry, let me add that again. 6 zeros, my apologies. 6 zeros, which is actually this number right here, and then you get this final product. Yeah, it's pretty frustrating trying to do this without a board. Here is the flow diagram that I just went through. When you start, you put the multiplicand up here and the multiplier down here. You test that multiplier sub-0, aka the last bit of the multiplier. If it's 1, you add the multiplicand and the product and place the result back into the product register. If it's 0, you don't do that and you just shift the multiplicand up by 1 and you shift the multiplier down by 1. That simulates the moving over to the left, so to speak, over here. Since it's a 32-bit multiplication, you do this 32 times until you've done 32 times, and then your product is over here, and you're done. Okay, a couple things I mentioned here with this type of multiplier. This is a multiplier, it does work, but the first issue, oh, by the way, we're not doing this in Verilog. You just need to understand how this works. The first issue is, notice that we have a 64-bit ALU, and if you recall from your Ripple carryout, the 32-bit one definitely can take a long time, so 64-bit is going to take even longer. So it would be nice if we can get rid of that 64-bit ALU. Also, the multiplicand is 64 bits. It'd be nice if we could keep that to 32 bits as well. And we can, by simplifying, well, they call it optimized multiplier, or a simplified multiplier. I wouldn't call this fully optimized, but it's more optimal than the previous one. Notice that the multiplicand stays the same, 32 bits. The ALUs become 32-bit, and the product is still 64. Now, the product does have to be 64 because that's our final answer. But what's going to be different is, notice we don't shift the multiplicand, but the product is being shifted right. The reason why this is complicated, and are they telling me? Nope. So what's going on in this one is the multiplicand goes here. The multiplier actually goes in the upper 32 bits. Okay? So what's happening is you're going to shift it right one. You're going to, hold on, I told you that incorrectly. Let me start over. Completely wrong what I just told you. The multiplier is stored on the lower 32 bits. Lower 32 bits is where the multiplier is. The reason for that is it's going to test that last bit to the control test. And if it does pass, it's going to add the multiplicand to the top half of the product. And then it's going to shift the whole thing to the right. What this does is the first time, if you think about this, let's say on that first example, where we were trying to get that 1000 in, and it is 1, we're just going to worry about that. You take the 1, you shift it, of course, product 0 at that time, and you put 1000 here. Well, remember, this is going to be shifted 32 bits, so eventually this will be shifted all the way down over here. So the reason why this works is because it's taking advantage of the fact that you're not going to use the lower half of the product until you've actually filled out the entire multiplier. So the idea is that you just use the lower half to right shift for the multiplier, still use the 32-bit, but only operate on the top half of the product, and then you shift it down. Another way to think about why this works is notice that over here in our old school multiplication, we shift everything over. Well, that's why you can think of it as that 32-bit ALU is only focusing on the 32 bits that actually matter at the moment, and then it right shifts everything down as necessary. And so that last add will be in the upper half of the product. Alright, I know that was a lot. You may need to review the book. The book does go through a couple examples here, as well as your homework will go over this as well. An even faster multiplier, although this is where things get a little interesting, is one where instead of doing this whole looping structure right here, you just take a bunch of 32-bit adders and you just chain them all together. So notice that we have the multiplican, and you're going to add the right input to all the ones on top is the multiplican, and then the one to the left is the bit of the multiplier. And so the idea is that if the bit of the multiplier is on, then you add the multiplican, otherwise you add 0. So notice that's why they put it as 0. So in other words, the first entry here is multiplier 0 times multiplican, aka if it's on, add the multiplican, otherwise you add 0. This is for multiplier 1, aka bit 1 times the multiplican. So if that's on, you add it to this 32-bit adder as well. And so what happens is that, let's see, so you take the 31-bit by the multiplier, and then you tailor or you peel off that 1 bit on that side. And so every time you go down these products, you peel off 1 bit to the final product until you come down here. So the question is, how many levels of these 32-bit adders are there? Well, if you notice, at each level you're peeling off 2 bits, okay? And it's going to be a 64-bit answer. So if you're peeling off 2 bits, it's not actually, let's see, so it'd be 64, then 32, etc., etc., 32, I'm sorry, 64, 62, wow, 60, 58, etc., etc. So you may think it's 32, but keep in mind that at the bottom you have this one last 32-bit multiplier, which does break out and give you the final 32. So it's actually 32, 32 then a 30, because you had this final 32-bit add happens at the end and gives you all the 32s in the middle. So it ends up being about 16 levels of these adders, and 16 levels of these adders. So it's a lot of adders still, and if you think about this, the area for this is going to be consume a lot of area, but it's going to be the fastest because you're simply pushing all the possible additions straight through. The other nice thing about this is it can be pipelined. What that means is you can start one multiplication right here, and then when that multiplication is down to the next level of ALUs, you can actually start another multiplication right behind it. So you can have up to 16 multiplications going at the same time, which can be very or highly advantageous. We'll talk a bit more about pipelining when we get to the next processor, but for now, keep in mind that the two that you're really going to want to keep aware of are the optimized multiplier and the naive multiplier. Alright, so we do want to talk a little bit about MIPS. We did not go over multiplication too much, but most multiplication does work the same way, where you'll have for a 32-bit application, you'll have a high and a low register. So this is a 32-bit MIPS, and it'll have two 32-bit registers, one for a high 32, the other for the low. So when you multiply two numbers, you can get MF high to get the high register and MF low to get the low register. I know that looks like M flow, but it's MF low. And then that way, once you do a multiplication, you can actually get the two highest and lowest. All right, let's pause for a moment and get to division.